Alright, so let's pick up with air masses circulate globally. Okay, so the atmosphere is in constant motion. That should say it. It is not static. Okay, the atmosphere is in constant motion. It's not static. Alright, the equatorial region receives the largest annual input of solar radiation. And I already said why, and that has to do with the tilt of the Earth on its axis. Okay, so warm air rises because it is less dense. It is less dense than cool air above it, than the cool air above it. So air is heated at the equator region, rises to the top of the atmosphere, establishing a zone of low pressure at the surface. Okay, so that's like when they talk about on the weather, you see like, oh well, there's an area of low pressure, there's an area of high pressure, and you might not really understand why they're saying that, but basically what they're saying is that the warm air rises above is less dense than the cool air above it. Okay, and the air heated at the equator region rises to the top of the atmosphere, establishing a zone of low pressure. Okay, remember, warm air rises, okay, cool air sinks. And more air rising beneath it forces the air mass to spread north and south toward the poles. Okay, so as air moves toward the poles, it cools and sinks. The sinking and rising surface air pressure the sinking air rises, surface air pressure creating a high pressure zone. Okay, so since the Earth spins on its axis, air masses in the northern hemisphere are deflected to the right, clockwise. Okay, so sort of what I'm saying here is that the warm air at the equator rises, okay, and that creates areas of low pressure, okay, or regions of low pressure. And the cool air sinks, creating regions of high pressure. Alright? And now those circulate, and the reason they circulate is because the Earth spins on its axis. Okay? So the masses in the northern hemisphere are deflected to the right, clockwise, and the southern hemisphere to the left, counterclockwise. As a result, it creates a series of belts of prevailing winds. Okay? So solar energy, wind, and the Earth's rotation create ocean currents. So this is how the ocean currents are created, and the global pattern of prevailing winds plays a critical role in determining the major patterns of surface water flow in the Earth's oceans. So obviously everything kind of is interconnected here. Okay, the global patterns of prevailing winds affect the ocean's currents. These systematic patterns of water movement are called currents. Okay, and you might have heard that. Everybody's probably heard that. The systematic patterns of water movement are called currents, and the major currents of the ocean generally mimic the movement of wind current. Okay, so the ocean currents mimic the wind currents. I mean, so again, interconnected is here, and until they encounter continents, of course. So as soon as they encounter land masses, the ocean currents change. So each ocean is dominated by two great circular water motions, or gyras. Within each gyra, the ocean current moves clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Along the equator, trade winds push warmer surface waters westward. The westerly winds produce eastward moving currents. Okay, so the westerly winds produce eastward moving currents, and at the equator, the trade winds push warm waters westward. Alright? Now, those things are not insanely important, but this is. Temperature influences the moisture content of air. Okay? So air temperature plays a critical role in the exchange of water between the atmosphere and the Earth's surface. So we know that there's an exchange of water between the atmosphere and the Earth's surface. Whenever matter changes from one state to another, energy is either absorbed or released, and we know that from chemistry. The amount of energy released during a change in state is called latent heat. So in going from an ordered state to a less ordered state, energy is absorbed, and it's opposite for going from a less ordered state to a more ordered state. So anytime you're going from a more ordered state to a less ordered state, energy has to be absorbed, okay? And if you're going from a less ordered state to a more ordered state, then energy is released, okay? So the transformation of water from liquid to gas is called evaporation, and the transformation of water vapor from gas to liquid is called condensation. When the rate of evaporation is equal to the rate of condensation, the air is said to be saturated. Okay, so that's important. So when the rate of evaporation is equal to the rate of condensation, the air is said to be saturated. The amount of pressure water vapor exerts is independent of the pressure of dry air. Okay, is called vapor pressure. So that's important. So the amount of pressure water vapor exerts independent of the pressure of dry air is called vapor pressure. Okay, and the units of vapor pressure are megapascals, MPa. The water vapor content of air at saturation is called saturation vapor pressure. Okay, so the water vapor content of air at saturation is called saturation vapor pressure. This is also known as water vapor capacity of air and cannot be exceeded. Okay, cannot be exceeded. So warm air has a greater capacity for water vapor than does cold air. And the amount of water in a given volume of air is its absolute humidity. Okay, so the amount of water in a given volume of air is absolute humidity. The more familiar measure to most of us, though, is called relative humidity, or the amount of water vapor in air as a percentage of the saturation pressure. Okay, so that would be like current vapor pressure over saturation vapor pressure multiplied by 100. So if air cools while the actual amount of moisture holds constant, then relative humidity increases as the value of saturation pressure declines. Okay? If the air cools to a point where the actual vapor pressure exceeds the saturation vapor pressure, then moisture in the air will condense and form clouds. As soon as the particles of water or ice in the air becomes too heavy to remain suspended, precipitation falls. So that's how this all works out. That's how precipitation occurs and why it occurs and how it relates to relative humidity. Okay? And the influence of temperature, obviously, on these factors. So for a given water content, or parcel of air, the temperature at which saturation vapor pressure is achieved is called the dew point temperature. So we've all heard of dew. We've all seen dew on our lawn during the fall as the air cools at night. So as nightfall approaches, temperatures drop and relative humidity rises. If cool night air temperatures reach the dew point, water condenses to form dew, lowering the amount of water in air. Okay, and as the sun rises, air temperatures warm and the water capacity increases. As a result, the dew evaporates, increasing vapor pressure in the air. All right. And here's precipitation has a distinctive global pattern. So when you first look at the pattern or distribution of precipitation, it doesn't look like it has any kind of specific situation. It doesn't look like it's specific at all. It just looks random. But by bringing together the patterns of temperature, winds, and ocean currents, we can understand global patterns of precipitation. Okay? And naturally, precipitation is highest in the regions by the equator, or the regions of the equator, declining as you move north or south. So as you move towards the North Pole or the South Pole, the amount of precipitation is decreasing, okay? And it's highest at the equator. But the decline is not continuous, okay? There are two peaks occur in the mid-latitudes, followed by a decline towards the poles. So they're sort of like a, maximum in the middle by the equator, maximum precipitation by the equator, then sort of like an intermediate region where the levels are actually going sort of against this gradient that I'm talking about, where there's going to be more precipitation, and then it declines sharply again as you move towards the poles. So the patterns result from patterns of rising and falling air masses associated with the belts of the prevailing winds. So as warm trade winds move across the tropical oceans, they gather moisture. Okay? Near the equator, the northeasterly trade winds meet the southeasterly trade winds. Okay? And this narrow region where the trade winds meet is the intertropical convergence zone. okay, and that's characterized by the high levels of precipitation. So this, if you wanted to know where the intertropical convergence zone was, or ITCV, it's characterized by the high levels of precipitation, and it's where the trade winds meet up, okay? Having lost most of the moisture, okay, the ascending air mass continues to cool as it moves northward and southward. Because the saturation vapor pressure rises, it draws water from the surface through evaporation, causing arid conditions, such as those found in a desert, might be an example. Okay? And one other pattern worth noting is that rainfall is greater in the southern hemisphere as compared to the northern hemisphere. Okay, that's because oceans cover a greater portion of the southern hemisphere. And water evaporates more readily from water surfaces, okay? So water evaporates more readily from water surfaces as opposed to dry surfaces. And this is also the reason why interior parts of continents experience less rainfall, okay, because they're dry surfaces, they're not water surfaces. If you're near the coast, you get more rainfall. Kind of a simple and intuitive concept. So another interesting aspect is the topography influences regional and local patterns of precipitation. So this is particularly pertaining to mountainous regions, and they influence local and regional patterns of precipitation, okay? Because mountains intercept airflow. And as the mass reaches a mountain, it ascends, cools, becomes saturated by water vapor, and releases much of its moisture at the upper altitudes of the windward side. So what I'm saying by windward side, I'm saying the side that these trade winds and these different wind patterns that we've discussed so far are hitting the mountain. So if it's hitting the mountain, or if the winds are moving into the mountain, then the air is going to ascend, cool, become saturated with water vapor, and release much of that moisture on the upper altitudes on that windward side. Okay, the phenomenon is known as rain shadow. But as the cool air descends the leeward side, so as the cool air descends the side that's not being hit, but as a result, the windward side, okay, of the mountain supports denser, more rigorous vegetation, more life, more animals live there.
And this leeward side, okay, is drier and more desert-like. It just has, I mean, it's really strange. It's a strange phenomenon. But check out a mountain that's, you know, hit by wind, or I think you could check out the Rockies or anything like that, and you'll be able to see that the one side, the side that's being hit with the wind, is actually, or that's running into the wind, or the wind's running into it rather, is actually really dense vegetation. Okay, there's a lot of vegetation, a lot of life. It looks very much like a forest maybe, and there's rainfall and everything there. And if you get to the other side, there's like, it's very low-lying plants, not a lot of life, not a lot of animals. Just a really stark contrast. You can also see this really on the Hawaiian Islands. So check out the Hawaiian Islands, check out some pictures. You'll be able to see what I'm talking about. So there's also irregular variations in climate, and the interaction between two components of the climate system, the oceans and the atmosphere, are associated with a number of climate variations that occur on a regional scale. I'm not going to go into what those are. I don't think they're all that important. So the next part here says most organisms live in local conditions that do not match the general climate profile of the larger region surrounding them. Okay, the conditions vary depending on the specific environments, the conditions vary depending on the specific environments, whether they are underground versus on the surface, okay, or beneath vegetation or exposed to soil. So that makes completely intuitive sense. If I'm underground, if I'm underground, my conditions are going to be different than if I'm on the surface. And the same thing if I'm beneath vegetation, meaning I can't get as much light and I'm beneath this green, this canopy, this forest canopy, or, and I'm not on exposed soil, it's going to be different than for the animals or organisms that are living on exposed soil. So these are microclimates, okay? These are microclimates that define conditions in which organisms live. So light, heat, moisture, and air movement all vary greatly, okay, from one landscape to another, accounting for a wide range of localized climates.